So work is a scalar quantity. The units are joules or newtons times meters and kilograms. Meters per second squared. If we replace the newtons times meters will give us kilograms meter squared per second squared, which is the same units as the units of the energy. And this brings us into the concept, very important concept of physics, that is a work is equal to the change of energy. So if you are dropping an object from a certain height, the object is changing its potential energy. So the change of potential energy is equal to the work done by force of gravity. Now, work as a formula for work, what do you have in your formula sheet is something like this: force times displacement times cosine theta. Personally, I don't like this because it is what is, you have to remember what is angle theta. What I recommend you keep in mind is that work is the product of the component of the force along the displacement, magnitude of the component of the force along the displacement, times the displacement. Why am I saying this? Because let's say that we have a situation like this. You have a horizontal surface and you have an object with mass, let's say 10 kilograms, that is moving with a force applied like this. Now, as a result of this, the object is moving for 5 meters as a result of this force applied. First of all, it's not only this force that the object is experiencing. If we draw the free body diagram of this object, we will have force of gravity, we will have force normal, and we will have a force applied. And we are assuming here that the coefficient of the friction is 0, so we are dealing with a frictionless surface. So now each of those forces has the ability, quote unquote, to do work. Now, the displacement is on this direction. So now what we have is the work done by force of gravity is the component of force of gravity along the displacement times the displacement. The component of force of gravity along the displacement is equal to 0 times 5.0, then this will be 0 joules. So force of gravity in this case is not doing any work on this motion. And then when we do what is the force of work done by force normal, then we go force normal times displacement, or the component of force normal along the displacement times the displacement is equal to the work done. So 0 times 5 meters is equal to 0 joules. So force normal doesn't do any work on this situation. However, the work done by force applied will be whatever is the component of force applied along the displacement times the displacement, and this will be, since they are in the same direction, then the component of this force is whatever is it. So let's say that is 10 newtons, and then we will have positive 10 newtons times 5 meters equals to positive 50 joules. So this is the work done on the object by this force. And the work net is the work done by each force. The work force normal and the work by force applied. So 0 plus 0 plus positive 50 is equal to positive 50 joules. And you can even figure this out by using the fact that force net, or verify this, using the fact that force net is 10 newtons in the positive direction times 5, that is the displacement, will be positive 10 times 5 equals to positive 50 joules. So you can verify it both ways. Now this makes a lot of sense when we are dealing with a situation. This method that I just explained makes a lot of sense when we are dealing with a situation that, let's say, force applied is with a certain angle and we have a friction of coefficient of the friction of 0.10. So let's say that the angle here is 30 degrees and the magnitude of this is equal to, let's suppose, 200 newtons. So mass of the object is 10 kilograms, just for simplicity. And then we start by drawing the free body diagram. So this being the situational diagram, and the free body diagram of this situational diagram will be whatever is force of gravity, that in this case is 10 times 10.81, will be 98.1 newtons. Then you have a force normal here. That is going like this. You have a force applied that is with magnitude of 200 newtons, but with an angle of 30 degrees with the horizontal. And then you have a force of friction here. So now let's say that as a result of this situation, the object is moving for 2 meters. So now we will find the work done by each of those forces and the work done by force net or work net. So we'll start with, first of all, let's figure out what is each of those forces. And in order to find that, we will use dynamics or components. So we'll have the horizontal and the vertical. So we'll have force of gravity. We'll have force applied, force normal, and then we'll move to force of friction. And since those are all the forces that the object is experiencing, we'll go to force net. So the horizontal component of force of gravity will be equals to 0. The vertical will be negative 98.1 newtons. Force applied, the horizontal will be 200 times cosine 30, and it is positive 173.2 newtons, and the vertical will be positive as well. So it will be 200 times sine 30, which is positive 100. Force normal in the horizontal is 0, in the vertical is positive force normal. Force of friction in the horizontal is negative force of friction, in the vertical is equal to 0. And then since the object is moving during east or along east, then we can say that the force net is equal to 10 times acceleration, and the vertical is equal to 0. From the horizontal, what we have is 173.2 minus force of friction is equal to 10 times acceleration. So this is the first equation that we have. And from the vertical, what we have is negative 98.1 plus 100 plus force normal equals to 0. And this is the second equation. As you notice here, we have 3 variables, A, force normal and force of friction, and 2 equations, but they are kind of hidden that actually we have 2 variables only. So from here, we can find that force normal is equal to 2, or whatever is 1.100 minus 98.1 is 1.9 newtons. So as you notice here, another thing is that force normal is not always equal to force of gravity. Force normal changes based on the situation that you are at. Okay? And from here, we can find force of friction as positive times 10. So force of friction is mu times force normal equal to 0.19 newtons. So now we have the equation 1 now has only one variable, because we will have 173.2 minus 0.19 is equal to 10 times acceleration. And from here we find that 173.2 minus 0.19 divided by 10 is the acceleration is 17.3 meters per second squared. Okay, so now that we have all the information that we need to, we can figure out the work done by force of gravity will be 0. The work done by force normal will be 0, because the work done by force of gravity, since we are dealing with the component of force of gravity along the displacement, and they are perpendicular to each other, then those are 0. The work done by force of friction will be a negative value, and the work done by force applied will be a positive value, because the components of force of friction along the displacement are negative, and the component of the force applied along the displacement is positive. And then the work net is the sum of all those forces, works, not forces, the sum of all those work, which is the same as saying the component of force net along the displacement times the displacement. So this is how you approach a question like this in work when we have work and energy. Questions? Now, if we go back to that important concept that we said in terms of the work and energy, then what helps us again into exploring that concept is that is known as the conservation law of energy. When we are dealing with the conservation law of energy, or what the concept of the conservation law of energy is, that the energy is not conserved, is conserved. The energy is conserved, is not lost or created, but it is transformed from one form to the other. A very typical concept application of the conservation law of energy is when we have a roller coaster. If we have a roller coaster, let's say something like this, then we have the initial here, let's say point A, and then this is the lowest point B, and then we have a certain point C, and then here is where the object is kind of moving with a constant speed. So now what do we have here? If we don't have any loss of energy as a result of friction, the gravitational potential energy that is calculated as mgh is the energy of the system, mechanical energy of the system, okay? Because mechanical energy of the system is the sum of kinetic energy and potential energy. Since the object is not having any kinetic energy here, the only mechanical energy that the object is possessing here is gravitational potential energy. This gravitational potential energy is the maximum energy, and it is transformed into, at point B, into kinetic energy, which will be the maximum kinetic energy. And when we have maximum kinetic energy, that means that we have the maximum velocity, because kinetic energy is 1/2 mv squared, and this since it is the maximum kinetic energy, will be the maximum velocity. At point C, you have both kinetic and potential, gravitational potential energy. Why? Because it is not quite at the top, at the point A, which means that you have some gravitational potential energy, but not everything. And then based on the conservation law of energy, that part that is not into a potential energy is transformed into kinetic energy. So if you know what is the height at point C, you can find what is the velocity at point C using the fact that the sum of the two, kinetic and potential at point C, is equal to mgh at point A. And then the same thing is here. It is kinetic and potential, gravitational potential energy. And if you know what is the velocity at point D, then you can find the height at point D, using the fact that the sum of the two is equal to either the gravitational potential energy at point A or kinetic energy at point B. This is a very typical question when there is no friction that is lost. If we have friction that is lost, then we have to take into the consideration that what is force of friction and what is the displacement, so that we can calculate the work done by the force of friction, and which will be the change of energy. So then we take away this energy done by the force of friction because it's transformed into heat or sound, or the energy of heat or sound or other types of energy. But based on the conservation law of energy, we have to take that into the consideration. This brings us into that is known as the simple harmonic motion. So now we have talked about motion a lot in Physics 20, and Physics 20, it's all about motion. So we start with kinematics, where we study the motion as the uniform, non-uniform motion when they are moving into a straight line. And then we move to the uniform circular motion. And even on kinematics, we see what is the relative motion and projectile motion. And then we move to the uniform circular motion. And then we see it as uniform in magnitude, but everything on direction is changing, which will produce acceleration, and then based on the second law of Newton, will produce a uniform, force net. And now we are talking about simple harmonic motion. So in order for a simple harmonic motion to be happening, you have to, any type of simple harmonic motion, you have to have two conditions. The first one is to have a periodic motion, which means that the motion is repeated. And the second one is to have a restoring force that is always toward the equilibrium. Those are the two conditions that we have in order to complete, for the object to complete a simple harmonic motion. Now, as a type of simple harmonic motion, we have two. We have pendulum and we have spring. So let's talk a bit about do we have a periodic motion? Do we have a restoring force in both of them, pendulum and spring? So when we have a pendulum, what we have is an object that is tied into a string at the wall, and then this is the equilibrium position. And what we are doing to this object is we are giving some gravitational potential energy. and then we are releasing it. Now, let's call this position O, this position A, and then what will happen as soon as we release it? The object will go to position A, or equilibrium, and then will go on swing on the other side of the pendulum. Now, in the ideal situation where there is no loss of energy based on the conservation law of energy, then we will have the same gravitational potential energy here. So maximum height, and this is maximum height as well. And then the object will, again, as it is reaching the maximum height, will go again to the equilibrium and then go swing on the other side at point A. So the motion that the object is obtaining will be point A, equilibrium point B, equilibrium point A, and so on. And under the conditions of conservation law of energy, this energy, as soon as we are giving it, will be conserved and transformed from kinetic to potential, from kinetic to potential, and so on. Based on this, what we will have is a periodic motion. So the first condition is satisfied. Let's take a look now if the second condition is satisfied. So we'll take the position A. So let's draw the free body diagram at A. What do we see in this case is the force of gravity that is always going down to the center of the Earth. And then we have a tension here. And we have a tension that is, starting from the object going along the string. So the tension will create a certain angle with the vertical axis, which means that we can break it down into a vertical component and a horizontal component. Now, since the object is not moving up and down, then those two forces are equal to each other. So force of gravity is equal to tension on the vertical, which is equal to T times cosine theta. That is the angle theta here, or theta here, is the same angle. And then the horizontal component, which is T times sine theta, is the unbalanced force, which means that this is a force net. And if you draw the free body diagram at any point on the right side of the equilibrium of the pendulum, you will always see that force net will be toward the equilibrium. Okay, this being the equilibrium, toward the equilibrium. This force net will be always to the equilibrium. And even if we do the same situation at point B, so let's do now draw the free body diagram at point B. What we will see is something like this. Force of gravity is going down. Tension is along the string. So it is creating an angle theta, which will break this tension down into a vertical component and into a horizontal component. So since it is not going up, it's not moving up, then force of gravity will be equals to the vertical component, which is T times cosine theta, and the horizontal component, which is T times sine theta, will be unbalanced force, which in terms of the third law of Newton is equal to force net and the equilibrium, and this will be toward the equilibrium as well, because the equilibrium at point B will be at this area here. So the two conditions that need to have a simple harmonic motion are satisfied at the pendulum. Let's take a look at the spring. But do you have any question in regards to that? Okay, so when we are dealing with a spring, I will just draw a spring here on different situations. So let's say that we have a spring and no mass is hanged into the spring. What do you have is that is the original length of the spring. So if you go and buy a spring at Home Depot or something like that, then you will see what is the length of the spring without any mass on it. Then what do? Is you hang a mass and you wait for the equilibrium to be reached. So as soon as you hang a mass, then you see that there is an extension, but then the equilibrium is reached, and this will be the equilibrium for the spring. On this case, what do you have is you have a force of gravity that is always going down to the center of the earth, and then you have another force which is known as the force of spring. The force of spring, based on the Hooke's law, is negative kx. So now, from this length that the spring was, what is happening? The spring is stretched at a certain length, and this is the x that the spring is stretched. Now it's final minus initial. Okay, so now the force of the spring is the opposite to the stretch. That means that if you are expanding, the force of the spring or the spring itself will exert a force to be compressing. And if you are compressing, then the spring will exert a force to extend it. Always the force of the spring is in the opposite direction with the what you are doing to the spring. If you are compressing, then will expand. If you are expanding, then will have the tendency to compress. So in this case, so what do you have is force of gravity is equal to force of the spring, which means that mg is equal to kx in magnitude. Okay, but then what do we do here is we give spring a certain extension. So after it reaches the equilibrium of the mass, then we give spring a certain extension here. Okay, this one it's known as the amplitude or maximum stretching of the spring. Okay, and then we are releasing. What do we notice in this case is that the spring goes up and down along the equilibrium. And if it is in an ideal situation where no loss of energy is happening, then the spring will be moving up and down forever. Now, based on the conservation law of energy, the elastic potential energy of the spring that we are giving here, it will be transformed into kinetic as we are moving to the equilibrium, and then elastic potential energy as it is compressed, and then kinetic, and then elastic potential energy as it is expanded, and so on. So what you will see is something like this. This satisfies the fact that we have a periodic motion. And if we do the free body diagram at either this situation or the top or the bottom of the expansion or compression of the spring, then we will notice that we will have a force of the spring that is an unbalanced force that will be toward the equilibrium position. So in both cases, the two conditions to have a simple harmonic motion is satisfied. Now, how do we solve those kind of problems using the conservation law of energy? When we have the pendulum at point A, what we have is maximum gravitational potential energy. At point O, what we have is maximum kinetic energy. And at point B, same as point A, we have maximum gravitational potential energy, which is the mechanical energy of the system. And then at any point in between, we have both. We have kinetic and we have potential. And then based on the information that is given, then we can find either what is the speed or what is the height of that you will have. But in any case, the height will not exceed the maximum height, or the speed will not exceed the maximum speed. And when we have a spring, the maximum x is, which is the amplitude, will be the maximum elastic potential energy. And as it is going to the equilibrium, we will have maximum kinetic energy. And when we are at the highest point, kind of lowest point, highest point, we will have maximum elastic potential energy. And the elastic potential energy is calculated as 1/2 kx squared. So it doesn't really matter if x is positive or if x is negative, because on both cases, what we will have is squaring it up. Positive to the power of 2 is positive, negative to the power of 2 is negative. And here we will have again kinetic maximum, or here kinetic maximum, and here on those 2 points we will have maximum elastic potential energy, which will result into maximum expansion or compression. And at any point in between, we will have both kinetic and potential, which is equal to either the maximum elastic or maximum kinetic. This is the same thing. And from there, we will find whatever is x and whatever is v. But again, even on this case, the maximum or x and v will not exceed the maximum speed or maximum expansion or compression or the amplitude. Is this clear?